Alright, let's talk about the universe. It's a place of unimaginable scale, stretching far beyond what our eyes can see or our minds can easily grasp. It's big, mysterious, and full of surprises, like black holes, the heavyweight champions of the cosmos. These cosmic titans are so dense, not even light can escape their pull. But what if there's a smaller, stranger kind of black hole, not the giants that swallow stars, but their tiny, almost invisible cousins, hiding in the shadows of the universe? Imagine a black hole no bigger than an asteroid, a bite-sized piece of space-time weirdness. These miniature black holes could be scattered throughout the cosmos, waiting to be discovered. These are called black hole morsels, a new idea inspired by Stephen Hawking's legendary work. Hawking's theories opened the door to the possibility that black holes come in all sizes, not just the massive ones we usually imagine. Think of them as cosmic crumbs left over from the universe's most violent events, like the explosive deaths of stars or the chaotic moments after the Big Bang. They might bridge the gap between the world of the very big, relativity, and the very small, quantum mechanics. These morsels could be the missing link, connecting the physics of galaxies to the mysteries of atoms. Physicists believe these morsels could be the key to uniting our greatest theories. If we can understand them, we might finally solve some of the deepest puzzles in science. If we find one, it could change everything we know about the universe. It would be a discovery that rewrites textbooks and reshapes our understanding of reality itself. So buckle up. We're going on a cosmic safari, hunting for the smallest, most elusive game in the universe. The search will take us to the frontiers of science and imagination. This isn't just about new objects, it's about pushing the limits of our knowledge, daring to ask questions no one has answered before. The story of black hole morsels is just beginning, and you have a front row seat. Get ready to explore the unknown, where every discovery could change the way we see the universe forever. So what are these black hole morsels? Let's get specific. When we talk about black holes, most people imagine monstrous objects devouring stars and warping entire galaxies. But these cosmic morsels are something entirely different, far smaller, yet just as fascinating. Unlike supermassive black holes, these are lightweights, masses closer to a large asteroid or small moon. Imagine something with the heft of a mountain, but not even close to the size of one. They're cosmic underdogs, hiding in the shadows of their gigantic cousins. They're incredibly dense, but on a cosmic scale, they're tiny. Picture an object so compact it defies our everyday understanding of matter. How do such strange things come to exist? One idea, cosmic collisions like neutron stars smashing together. When these titans meet, the energy released is unimaginable and the aftermath can be just as wild. The aftermath could create fragments of super dense matter that collapse into these tiny black holes. These fragments, left over from the chaos, might be the seeds of these miniature monsters. Another theory, when two black holes merge, tiny droplets of space-time might pinch off, forming independent asteroid-mass black holes. It's like the universe itself is sculpting new objects from the fabric of reality. These morsels would wander the galaxy, silent and invisible. They'd drift through the Milky Way, passing through stars, planets, and even us without leaving a trace. To grasp their scale, a black hole with the mass of a large asteroid would be smaller than an atom. It's almost impossible to imagine. All that weight, squeezed into a point you could never see. That's the mass of a mountain, compressed into a space tinier than anything a microscope could see. It's a level of density that breaks our intuition, challenging what we think is possible. We're not talking about a small rock, but a point of infinite density. A miniature puncture in reality. It's a place where the known laws of physics are pushed to their limits. They are pure gravity, pure space-time curvature, in a tiny, elusive bundle. Their gravitational pull is intense, but their size makes them nearly impossible to detect. And it's this small size that makes them so interesting, and potentially revolutionary. If we could find them, they might change everything we know about the universe. If they exist, they could reveal secrets about the universe's most extreme events. They might even help us understand the earliest moments after the Big Bang, or the true nature of dark matter. And maybe, just maybe, they'll help us unlock the next great leap in physics, opening doors to mysteries we haven't even dreamed of yet. Enter Stephen Hawking, a brilliant physicist whose ideas would forever change our understanding of the universe. In the 1970s, Hawking made a groundbreaking prediction that challenged everything we thought we knew about black holes. By combining Einstein's theory of gravity with the strange rules of quantum mechanics, Hawking realized something astonishing. Black holes aren't completely black. Instead, they emit a faint glow, a whisper of energy leaking out into the cosmos. This mysterious glow is what we now call Hawking radiation, a phenomenon that bridges the worlds of the very large and the very small. But how does this strange radiation actually work? In quantum mechanics, what we think of as empty space is anything but empty. Instead, it's a bubbling sea of virtual particles constantly flickering in and out of existence, like tiny flashes of energy that appear and vanish in the blink of an eye. Sometimes a pair of these particles pops into existence right at the edge of a black hole's event horizon, the point of no return. If one particle falls into the black hole while the other escapes, the escaping particle becomes real, carrying energy away as Hawking radiation. The black hole, in turn, loses a tiny bit of its mass. Over unimaginable timescales, this process causes black holes to slowly evaporate, shrinking ever so gradually as they emit this faint radiation. For massive black holes, though, Hawking radiation is incredibly weak, so faint that it's utterly drowned out by the cosmic microwave background, the afterglow of the Big Bang. Trying to detect Hawking radiation from a stellar mass black hole is like trying to hear a pin drop at a deafening rock concert. Virtually impossible with our current technology. For decades, this beautiful and elegant theory has remained just that, a theory with no direct experimental evidence to confirm it. But what if there's a way to make Hawking's bold prediction testable? To finally catch a glimpse of this elusive radiation? That's where the idea of black hole morsels comes in, tiny, hypothetical black holes that could emit much stronger Hawking radiation. Because of their minuscule size, these morsels might just be the perfect candidates for finally detecting Hawking radiation and proving Hawking's theory right here on Earth. Here's the twist. Hawking's theory says the smaller the black hole, the hotter and brighter it is. While giant black holes are cold and quiet, tiny morsels would blaze with energy. Think of a bonfire versus a firecracker. The morsel is the firecracker, burning fast and bright. These morsels would emit intense radiation, not visible light but high-energy gamma rays and exotic particles. In their final moments, they'd unleash a brilliant burst of gamma rays, a cosmic death cry. So instead of searching for a whisper from a giant black hole, we can hunt for the loud shout from a tiny one. If we find one, it would confirm both a new type of cosmic object and Hawking's most profound prediction. It would be a Nobel-worthy discovery, rewriting our understanding of the universe. These morsels are our best shot at directly observing Hawking radiation. The search is on for these cosmic firecrackers. If we catch one in the act, it could change physics forever. The universe might finally reveal one of its deepest secrets. So how do we find these black hole morsels? Regular telescopes won't cut it. We need specialized detectors for the universe's most powerful particles, gamma rays. Enter HESS in Namibia, an array of telescopes that spots faint flashes of Cherenkov light from gamma rays hitting our atmosphere. Then there's HAWK in Mexico, using massive water tanks to catch the same flashes and pinpoint cosmic explosions. LASSO in China combines water tanks and ground detectors, making it ultra-sensitive to the highest energy gamma rays. These observatories scan the sky for the telltale burst of an evaporating black hole morsel. If a morsel is out there, these machines are our best hope of catching its final brilliant flash. They're our cosmic sentinels, watching for signals from the quantum edge of space-time. The hunt is global, and the technology is cutting edge. All we need is one unmistakable signal to change everything. Imagine one of these observatories detects a burst matching the signature of a black hole morsel. It would be a scientific revolution, proof that Hawking radiation is real. This would be the first experimental evidence linking gravity and quantum mechanics. It could help us build a unified theory of everything, the holy grail of physics. Studying these morsels might reveal hidden dimensions or even clues about the true nature of space and time. And there's another mystery: dark matter. Some theories suggest primordial black holes could make up part of this invisible mass. Finding morsels would give us a new way to investigate dark matter and the universe's missing mass. The implications would ripple across physics, cosmology, and beyond. One discovery could unlock answers to the universe's biggest questions. But let's be real, finding a black hole morsel is incredibly tough. We don't even know if they exist or how many are out there. If they're rare, we might search for decades and find nothing. The high-energy sky is crowded with many sources of gamma rays, pulsars, blazars, and more. The final burst from a morsel would have a unique signature, but it could be faint or easily confused. Astronomers must rule out every other explanation before claiming a discovery. We need sharper theoretical models and even more sensitive detectors. The hunt is a marathon, demanding patience, ingenuity, and relentless curiosity. But the potential payoff makes the challenge worth it. So, what's next? The search combines theory and observation. Scientists use supercomputers to simulate cosmic collisions and predict the exact signature of a Morsels evaporation. These models guide telescopes on where and what to look for. New observatories like the Cherenkov Telescope Array will be even more sensitive, scanning wider swaths of sky. The search's multi-messenger gravitational wave detectors like LIGO can spot mergers, then gamma-ray telescopes can watch for Morsels. By combining data from different detectors, we maximize our chances of discovery. The future is bright, and the hunt is just beginning. With every new tool, we get closer to unlocking the universe's secrets. Why do we search for black hole Morsels? Because it's in our nature to explore. This quest is about pushing the boundaries of knowledge for the sheer joy of understanding. Whether we find them or not, the journey yields rewards. New technology, better data analysis, and inspiration for future scientists. Discovering a morsel would be a philosophical leap, proving the universe is even stranger than we imagined. It would show that the same quantum laws shaping atoms also govern the death of black holes. We'd know more than ever that we're made of stardust, and capable of understanding the stars. So next time you look up, remember, the darkness might be hiding cosmic morsels burning with Hawking radiation. The hunt is on, the telescopes are watching, and one day we might unlock one of the universe's greatest mysteries. In searching for black hole morsels, we learn more about the cosmos and ourselves. Keep looking up.